10 radio dishes spread across America, from Hawaii to the Virgin Islands, have been watching objects that appear to cross the sky at nearly 50 times the speed of light. The equipment is not broken, and the measurements have been repeated for years. If those bright knots are really matter moving that fast, the problem is bigger than Einstein. Cause and effect can trade places, and a message can arrive before it was sent. So either nothing actually broke the speed of light, or the picture in front of us is not showing what we think it is. The speed of light is usually treated like the top number on the speedometer of the universe, roughly 300,000 kilometers per second, and that is where the road ends. You can push matter closer and closer to that limit, but every extra bit of speed costs more energy than the one before it. At some point, the problem stops looking like engineering and starts looking like a personal argument with the laws of nature. The limit matters for a deeper reason. It helps keep events in order. You flip a switch, then the lamp comes on. You drop a coffee mug, then the mug hits the kitchen floor. Then you remember exactly how much that tile cost. Cause comes first, effect comes second, and this simple arrangement keeps the world from turning into a filing cabinet full of events with the labels missing. A controllable signal moving truly faster than light would threaten that order. In some frames of motion, an answer could arrive before the question. A warning could be received before the event that produced the warning. You could receive a message telling you not to send the message that you have already received. The mathematics does not merely give you a faster spaceship. It gives you a headache large enough to include yesterday. That is why faster-than-light motion is not a small technical violation. It reaches into causality itself. If real matter or real information can cross that boundary in the ordinary way, the structure of time needs more than a tune-up. Someone has to open the whole machine, and black hole jets are where the machine appears to misbehave. A black hole is often pictured as a cosmic drain. Matter falls in, disappears. End of story. The interesting part actually begins before anything crosses the point of no return. Gas approaching the black hole usually has sideways motion, so instead of falling straight in, it spirals around the center and forms a wide rotating disk of hot material. That disk becomes hotter as matter moves inward. At high enough temperatures, atoms lose electrons and turn into plasma, a gas made of electrically charged particles. Plasma conducts electric current, creates magnetic fields, and reacts strongly to those fields. The region around an active black hole is therefore not just a gravity problem. It is gravity, electricity, magnetism, rotation, heat, and radiation all arguing at the same table. Some matter continues inward, some is caught in magnetic structures and accelerated away from the central region. Two narrow streams can emerge in opposite directions along the rotation axis. These are jets. Nothing is climbing back out from inside the black hole. Once matter crosses the event horizon, the outside world does not get it back. The jet is built from material that has not yet crossed that boundary. It gets close enough to enter a magnetic and gravitational machine that can redirect part of the flow outward at a speed just below the speed of light. That alone is strange enough. Matter is falling toward a black hole, while another part of the same environment is being fired outward with enough energy to cross an entire galaxy. Some jets stretch for thousands or hundreds of thousands of light years. They remain surprisingly narrow over distances where an ordinary stream would have spread into a useless cloud long ago. These jets can also change the galaxies around them. They heat gas, push material away from the center, and sometimes make it harder for new stars to form. A region smaller than the galaxy by an absurd margin can influence whether the rest of the galaxy gets the raw material needed to build future stars. The smallest office in the building somehow has the keys to the heating system. But the faster-than-light problem does not come from measuring the full jet. It comes from bright features inside it. A radio image of a jet is not always a smooth, glowing line. It contains bright knots, patches, and compact regions. Astronomers make an image, wait, make another image, and see that one bright feature has moved farther from the center. From the angular shift and the estimated distance to the galaxy, they calculate how far that feature appears to have traveled. The logic is familiar. A highway camera photographs a car at one point, and another camera catches it farther down the interstate. You know the distance and the time. Divide one by the other, and you have the speed. The cosmic version sometimes returns an answer that would get the highway camera sent back to the manufacturer. 3 times the speed of light, 5 times, 10 times, 15 times. In the long-running MOJAVE program, some apparent speeds reached almost 50 times the speed of light. MOJAVE uses the Very Long Baseline Array, one of the most remarkable pieces of astronomy infrastructure in the United States. 10 radio dishes sit across American territory from Mauna Kea in Hawaii to St. Croix in the Virgin Islands. Other antennas stand in Washington, California, Arizona, New Mexico, Texas, Iowa, and New Hampshire. The longest separation is roughly 8,600 kilometers. Each dish is 25 meters across. The signals are recorded and combined, so the array behaves like a radio telescope with a virtual size comparable to the distance between the antennas. The operation is coordinated from Socorro, New Mexico. In practical terms, astronomers have built a telescope whose pieces are scattered across a large part of the country, and this continent-sized instrument keeps returning impossible-looking numbers. Matthew Lister at Purdue University and the MOJAVE collaboration have spent years tracking bright features in hundreds of relativistic jets. Their studies show that most apparent speeds are far below the most extreme values, but a small number reach above 30 times the speed of light, with the fastest near 50. Many bright features do not even move in simple straight lines. They accelerate, change direction, or follow curved paths. That matters because an instrument error should not know how to imitate organized motion. The standard explanation begins with geometry. A jet that produces an extreme apparent speed is often aimed almost toward Earth, but not exactly at us. The bright feature is moving nearly at the speed of light, while also moving closer to the observer. Light emitted from the feature, at a later moment, therefore starts its trip to Earth from a point that is already closer. Imagine a car driving almost directly toward you at night while passing slightly to one side. The driver flashes the headlights once. The car keeps moving toward you and flashes them again. The first flash starts farther away, while the second flash starts much closer. Both light signals travel at exactly the same speed. The second flash does not catch the first. It simply has less distance to cover. The two flashes can therefore arrive closer together in time than the interval during which the car actually moved between the two positions. Now replace the car with a bright knot moving at nearly the speed of light. The effect becomes enormous. The knot emits light at one position. It races toward Earth and slightly across our line of sight. Later, it emits more light from a point that is significantly closer. The second signal starts with a major advantage. Astronomers see the sideways shift of the feature. They compare that shift with the short time between the arrival of the signals. The calculation can produce 5, 10, or 50 times the speed of light, even though the local motion of the plasma never crossed the light barrier. Nothing had to outrun its own light. The image did. For someone hearing this for the first time, the explanation can sound suspiciously convenient. The telescope reports an impossible speed. Physicists add an angle, account for light travel time, and the impossible speed disappears. Einstein survives another day. That naturally feeds a popular suspicion. Maybe the effect is called apparent only because modern physics has too much invested in relativity to admit that something broke the rules. There are careers built on established theories. There are grants, institutions, reputations, and textbooks. Scientists are human, and humans do not always cheer when somebody arrives on Friday afternoon and suggests removing the foundation under the building. The problem for the easy conspiracy version is history. British astrophysicist Martin Rees described the basic mechanism of apparent faster-than-light motion in the 1960s, before astronomers had convincing observations of the phenomenon in these jets. He showed that material moving close to the speed of light and aimed at a small angle toward the observer should appear to move across the sky faster than light. The explanation was not invented after an embarrassing measurement. The embarrassing measurement showed up later. That does not prove every interpretation of every jet is correct. It does mean the simple story of scientists seeing a forbidden number and inventing an excuse afterward does not fit the timeline. The supposed excuse had already been written before the crime. The model also predicts more than one number. A jet aimed toward Earth should look brighter than one aimed away from us. Variations in brightness should appear faster. Sources whose jets point close to our direction should be overrepresented among the brightest objects we detect. That is broadly what astronomers see. Black holes often produce two opposite jets, but images frequently show one side much more strongly. The jet moving toward Earth has its radiation boosted in our direction. The opposite jet can be dramatically dimmer, even if the two were launched as part of the same system. The universe is not aiming more jets at Earth than anywhere else. We simply notice the flashlight pointed into our eyes. An active galaxy with a jet pointed close to our direction is called a blazar. Blazars can change brightness rapidly and are some of the strongest examples of relativistic effects. Data from the Fermi Gamma Ray Observatory also show a relationship between gamma-bright active galaxies and faster apparent jet speeds, which fits the idea that direction and relativistic boosting are part of the same picture. At this stage, the case appears nearly closed. Matter stays below the speed of light. Geometry compresses the time between arriving signals. The jet appears faster than light, causality survives, and the speed limit remains on the books. Then a worse question appears. What exactly is the bright knot that we just measured? For most of this story, it is easy to imagine a compact blob of plasma moving down the jet. It was here in the first image, there in the second image, so the same material must have traveled between the two places. That assumption is not always safe. A telescope sees brightness. It does not see an identification tag attached to the plasma. A bright knot can be a wave moving through the jet. Think about a wave moving around a football stadium. Thousands of people stand up and sit down in sequence. The wave can travel around the stadium, even though nobody runs through the seats. The same basic idea can happen inside a relativistic flow. Plasma moves along the jet, while a disturbance moves through the plasma. One region brightens, then another region brightens farther down. From far away, the bright pattern moves as if it were one object. The particles do not have to make the entire trip together. A bright knot can also be a shock. A faster part of the flow catches a slower part. Material compresses. Particles gain energy, and a bright region forms. The shock can move at one speed while the individual particles move at another. The opposite can also happen. A bright knot can remain almost stationary while plasma races through it. Water flowing past a rock produces a persistent turbulent patch. The pattern can stay in roughly the same place while new water passes through continuously. Some jet structures behave in an equivalent way. The glowing region stays put, but the material is not sitting there. So a fast-moving bright knot does not automatically measure the speed of matter. A stationary bright knot does not automatically mean the matter is stationary. That single fact changes the entire mystery. The question is no longer only why a blob appears to move faster than light. The question is whether the blob exists as the kind of object we imagined. Observations of the blazer BL Lacerte have shown moving structures that can be understood as waves inside a relativistic jet. The overall flow is already moving extremely fast, while disturbances propagate through it. The observed motion can combine the motion of the jet, the motion of the wave, and the travel time of the light. The jet could answer our measurement with a very simple complaint: I did not outrun light. You compared two old pictures of me and decided that the bright thing in both pictures had to be the same thing. The problem becomes even more complicated when different telescopes observe the same jet. A radio telescope responds to one part of the particle population. An X-ray telescope responds to particles at much higher energies. Optical observations can emphasize yet another region. These instruments can all look at the same jet while tracing different physical structures. That is why one wavelength can show a slow component, while another reveals something much faster. Centaurus A has provided examples in which radio and X-ray features do not tell exactly the same motion story. The instruments do not have to disagree. They may simply be watching different pieces of a layered flow. Messier 87 makes this problem especially useful. The galaxy sits roughly 55 million light-years from Earth. At its center is the supermassive black hole whose shadow became the first black hole shadow ever imaged. Long before that famous picture, American astronomer Heber Curtis at Lick Observatory noticed a strange straight ray extending from the galaxy in 1918. At the time, it was a curious streak on a photographic plate. More than a century later, that streak is still causing trouble. NASA observatories have studied the jet across radio, optical, infrared, and X-ray light. A fresh analysis, using 13 years of Chandra observations, resolved new structure inside the jet. Some features are nearly stationary. Others show apparent faster-than-light motion, reaching roughly 4.8 times the speed of light. Same galaxy, same jet, very different speeds. The analysis also showed that unresolved components can blend together and bias a speed measurement. If two bright regions are too close for the telescope to separate cleanly, the image can treat them like one feature. One fades, the other brightens, and the center of the combined glow shifts. A moving center of brightness is not automatically a moving object. This is not a claim that all faster-than-light measurements are image processing mistakes. Many components can be tracked across multiple observations with strong confidence. The point is narrower and more uncomfortable. Before assigning a speed to a bright feature, astronomers need to establish what the feature physically represents. That is not always possible. The black hole system V404 Cygni showed a different complication. During a major outburst, its jets changed direction on timescales of minutes to hours. The inner accretion flow was likely tilted relative to the rotation of the black hole, causing the direction of the jets to swing. At ordinary speeds, a small change in angle is boring. Near the speed of light, it can completely rewrite the picture. A jet pointed a little closer toward Earth can suddenly appear faster and brighter. A small change in geometry can produce a large change in apparent motion without a dramatic increase in the actual speed of the plasma. This is why some jet features accelerate on images even when part of the change may be geometric. MOJAVE observations have found that non-straight motion and acceleration are common among well-tracked features. A relativistic jet is not a steel pipe firing identical bullets on a fixed line. It is a flow, and flows bend. There may not even be one single speed that describes the entire jet. The plasma can have one speed, a shock can have another, a magnetic disturbance can have another, a bright pattern can have another. These are not competing opinions about the same number. They are different physical motions. Relativity itself also tells us that speed has to be stated relative to something. We can ask for speed relative to Earth, relative to the host galaxy, or relative to material moving inside the jet. There is no universal cosmic highway patrol sitting motionless outside the universe with the final radar gun. That does not mean every answer is equally valid. It means the question has to be defined correctly before the number means anything. A deeper problem appears in some blazars that produce extremely rapid gamma-ray flares. Gamma rays are very high-energy light. If the brightness of a source changes in a very short time, the emitting region cannot be arbitrarily large because light itself needs time to cross it. The flare can also be so intense that without strong relativistic motion, gamma rays would interact with other photons inside the source and have trouble escaping. The physics then suggests a very fast flow moving strongly toward Earth. Yet, radio images of some of those same objects show slow or nearly stationary structures. One part of the evidence says race car. Another part says shopping cart with one bad wheel. Same jet. Researchers have several possible solutions. The jet may have a fast central spine surrounded by a slower outer layer. Gamma rays could come mainly from the fast interior, while radio images emphasize the slower exterior. The flow may also slow down as it moves away from the black hole. Or small fast regions may form inside a larger jet and briefly point toward Earth. Another possibility is that radio images are following a standing shock while fast plasma passes through it. Different objects may use different combinations. There is no single instruction manual that closes every case. That is the real white spot in this story. The standard theory explains very well how an apparent speed can exceed the speed of light. It does not always tell us exactly what physical process created the bright feature or how fast the underlying plasma itself is moving. The official explanation survived. The mystery moved. Even the composition of the jet is still not completely settled in every system. The word plasma sounds precise, but it can hide very different ingredients. Some jets may contain large numbers of electrons and positrons, the antimatter partners of electrons. Others may contain electrons and much heavier protons. That difference matters because protons carry far more mass. A proton-rich jet can transport much more kinetic energy than a jet dominated by electron and positron pairs. The composition can also change as the jet travels and picks up surrounding material. Nobody can fly a sample container into a quasar jet and bring it home. The answer has to be inferred from radiation, polarization, motion, and the effect of the jet on surrounding gas. The launching mechanism also remains an active area of research. Matter in the accretion disk rotates rapidly. Magnetic fields become twisted and organized. Some models extract energy from the disk, while others can tap energy associated with the rotation of the black hole itself through magnetic fields outside the event horizon. This does not mean particles are escaping from inside the black hole. The energy transfer happens outside the horizon. Messier 87 is one of the best laboratories for studying this region because its central black hole is massive, relatively nearby by galactic standards, and large on the sky. Very long baseline observations have resolved the base of the jet extremely close to the central object. Researchers can watch the flow widen, narrow, accelerate, and develop structure. That is an extraordinary view. It is not a complete repair manual. This gap between what is well explained and what remains uncertain is where alternative ideas have always entered. One of the most famous came from American astronomer Holton Arp. Arp argued for decades that some quasars might be much closer than mainstream cosmology says. The standard interpretation uses large redshift as a sign of great cosmological distance. Arp proposed that part of the redshift of some quasars could be intrinsic to the objects themselves. His version mattered directly to faster-than-light motion. A telescope measures angular movement on the sky. To convert that movement into a physical distance, astronomers need the distance to the source. If the source is much closer than assumed, the calculated physical speed becomes smaller. Same angular motion, different map scale. ARP was not an anonymous internet commentator. He was a professional astronomer who produced a famous catalog of peculiar galaxies and spent much of his career defending his interpretation. His ideas were rejected by the mainstream because the standard cosmological redshift picture explains a much larger body of evidence, and because the proposed physical associations between nearby galaxies and high redshift quasars did not hold up convincingly across the broader data. But the history matters. The alternative was real. Its scientific status is also clear. It did not win. That does not make the underlying lesson disappear. Every apparent transverse speed depends on a distance estimate. If the scale is wrong, the speed is wrong. Another family of alternatives questions whether the speed of light has always behaved exactly the same way under every possible condition. Physicist João Magalhães and others developed variable speed of light models in which light could have behaved differently in the very early universe. These ideas were proposed to address cosmological problems that are usually handled with inflation. They are legitimate theoretical physics, not evidence that black hole jets are currently firing matter above the speed of light. The distinction is important. A theory can allow unusual physics without a particular observation proving that theory. Researchers also test whether the basic symmetry behind relativity could fail by a tiny amount at extreme energies. They compare arrival times of photons with different energies from distant explosions. If high-energy light traveled at a measurably different speed, very distant events could reveal the difference. So far, there is no generally accepted evidence that ordinary light in these observations violates the expected limit. The speed limit is not protected by a security guard who refuses to let anyone test it. People keep trying. There are also tachyons, hypothetical particles that would always move faster than light if they existed. They have never been detected. A faster-than-light bright knot in a jet is not evidence for a tachyon because the standard geometric effect can produce the observation without any such particle. Ideas involving extra dimensions or shortcuts through space also appear in theoretical physics. A wormhole, if one could exist and remain usable, would change the path rather than simply force a local object through the light barrier. Again, black hole jets do not provide evidence for such structures. The names sound connected because they all involve faster than light travel. Physics does not work by matching words in a headline. Another alternative comes from the electric universe movement. Modern advocates such as Wallace Thornhill and Donald Scott argued that cosmic plasma and electric currents play a much larger role than standard astrophysics allows, and they often interpret jets as giant electrical structures. The first part of the observation is not controversial. Jets really are made of charged particles. Electric currents and magnetic fields really do matter. Modern astrophysical jet models would collapse without electromagnetism. The disagreement begins when the electrical part is promoted from an essential ingredient to the whole explanation. Mainstream models connect the jet to gravity, accretion, rotation, plasma physics, and magnetic fields together. Radical electric universe interpretations often try to reduce the role of the black hole or replace parts of the standard picture with large-scale electrical circuits. Then the burden gets much heavier. The alternative has to explain stellar motions near galactic centers, hot accretion flows, X-ray emission, the observed black hole shadow in Messier 87, gravitational effects, and a long list of other measurements. Finding one key does not mean the key opens every door in the house. Still, the electric universe idea remains popular partly because black hole jets genuinely look electrical. They are narrow streams of plasma threaded by magnetic fields. They carry enormous energy over huge distances. A person looking at the image without the rest of the evidence can reasonably ask why gravity gets top billing. That question is worth asking. The answer is not that electricity is ignored. The answer is that it is already inside the mainstream model. There is also the broader conspiracy argument that physics institutions protect Einstein because too much modern science depends on relativity. This version circulates constantly in online discussions around faster-than-light observations, quantum physics, and black holes. It survives because it contains one human truth. Institutions can be conservative. People can defend careers and reputations. Consensus can be wrong. Science history gives plenty of examples of ideas that were resisted before becoming accepted. But the leap from institutions can resist change to this measurement must be suppressed is much larger than it first appears. Relativity does not survive only because astronomers reinterpret distant jets. It works in particle accelerators. It works in atomic clocks. It works in satellite navigation. Your phone knows where you are, partly because engineers correct satellite clocks for relativistic effects. Without those corrections, the positioning error would grow quickly enough to become useless. A theory that helps get you to the correct exit on an interstate is at least doing something right. That still does not make the theory final. Newton worked extremely well before Einstein. Newton still works extremely well for bridges, cars, baseballs, and most things that do not travel close to the speed of light or live next to enormous gravity. Einstein did not erase Newton. He showed where the older description stops being enough. A future theory may do the same to Einstein. General relativity and quantum physics still do not fit together cleanly. There is no completed theory of quantum gravity accepted as the final description of nature. The inside of black holes and the deepest structure of space-time remain open problems. So it is entirely reasonable to think relativity may someday become part of something larger. The faster-than-light jet measurements simply do not force that conclusion yet. There is an even more speculative line that appears in discussions of advanced civilizations. A civilization far beyond ours might someday use rotating black holes as energy sources. The idea of extracting rotational energy from black holes has a real foundation in theoretical physics through processes related to the work of Roger Penrose. From there, speculation sometimes jumps to the possibility that extreme jets could be engineered. There is no evidence for that. No observed jet requires an artificial origin. Their spectra, variability, connection to accretion disks, and behavior across many systems are consistent with natural astrophysical processes. But the speculation tells us something about the image itself. A beam of energy extending across a galaxy looks designed. Human brains are very good at seeing a straight line and looking for the person holding the ruler. Nature does not need one. The most important point is not that every alternative is equally likely. They are not. Apparent faster-than-light motion caused by relativistic geometry is strongly supported. Intrinsic redshift models are outside the scientific consensus. Variable light speed models are theoretical possibilities in specialized conditions, not explanations demanded by these jets. Electric universe claims go far beyond what the evidence requires. Artificial jet ideas belong to speculation. Giving every version a seat at the table does not require giving every version the same size chair. The interesting part is where the mainstream picture itself admits uncertainty. We do not always know what a moving bright feature physically is. We do not always know whether pattern speed equals plasma speed. We do not know the exact composition of every jet. We are still working out how the central engine launches and organizes the flow. Those are real gaps. They are more interesting than pretending the speed of light has already been defeated. There is also a philosophical problem hiding inside the measurement. Astronomy never shows us the universe as it is right now. The moon appears to us slightly more than a second in the past. The sun appears roughly 8 minutes in the past. Nearby stars appear years in the past. Messier 87 appears as it was tens of millions of years ago. Every part of the sky comes with its own delivery delay. Usually that fact is harmless. A star does not move enough during the travel time between two nearby signals for our everyday intuition to collapse. A relativistic jet does. Near the speed of light, the delay itself becomes part of the motion we infer. That does not mean astronomy is fake. It means astronomy is reconstruction. A telescope collects radiation. Researchers measure position, spectrum, brightness, polarization, and timing. Then they build a physical model that has to explain all those things together. A good model does not get to fix one inconvenient speed and ignore everything else. It has to explain why one jet is brighter, why the opposite side is dimmer, why gamma ray activity is correlated with faster apparent motion, why some structures accelerate, and why others remain almost fixed. The more independent observations the model survives, the stronger it becomes, but it is still a reconstruction from delayed light. No astronomer is standing next to a quasar with a radar gun. That distinction becomes especially important when two bright features seem to move apart from each other. If one appears to move one way at several times the speed of light and another appears to move in the opposite direction, the separation rate seen on the image can become even larger. It is tempting to add the numbers and declare physics twice as broken. That is not how relative speed works in relativity. The apparent motions are calculated from signals arriving at Earth with their own geometry and delays. The rate at which two spots separate on an image is not automatically the speed that one spot would measure for the other locally. A pattern can spread faster than light without carrying information faster than light. Even a laser spot sweeping across a very distant surface can move across that surface faster than light if the geometry is extreme enough. No individual photon travels sideways with the spot. No message is being carried from one end of the moving spot to the other. The pattern moves. The material carrier does not have to. This same distinction is what makes black hole jets so easy to misunderstand. We see a spot. We assume an object. We see a new position. We assume motion of that object. We divide distance by time. We call the result speed. Every step sounds reasonable. Together, they can manufacture an object moving 50 times faster than light, even when no atom did anything forbidden. That does not make the number fake. The number describes something real in the observation. The mistake begins when we decide too quickly what physical thing owns that number. This is why the debate around these jets is more subtle than either side of the internet usually wants. The simple skeptical version says physicists are covering up faster than light matter. The simple establishment version says it is only an illusion, nothing to see here. Both are too easy. The standard relativistic explanation is strong. It was predicted before the clearest observations, and it explains multiple independent features of jets. There is no confirmed case here of matter or usable information locally outrunning light, but the word illusion can also hide too much. The bright structures are produced by real physics. The waves are real, the shocks are real, the plasma is real, the magnetic fields are real, the measured shifts are real. What remains uncertain in some cases is which physical process produced the moving pattern and whether that pattern moves with the material itself. So the telescope is not lying. The image is not fake. The number is not invented. The dangerous step is the story we attach to it. A century ago, Haber Curtis saw a strange straight ray sticking out of Messier 87. Today, NASA instruments can divide that ray into tiny structures and watch some of them appear to move faster than light. The improvement in technology did not make the mystery disappear. It made the mystery more precise. Now we know that one jet can contain fast features, slow features, stationary features, shocks, waves, bends, and changing brightness. We know that different wavelengths can emphasize different parts of the same flow. We know that geometry can produce impossible-looking speeds without breaking the speed limit. And we still have to ask what exactly moved. That is the part worth keeping. The speed of light has not fallen. Causality has not been caught leaving through the back door. Einstein has not been rescued by a last-minute excuse. What failed was something much more ordinary. Our instinct that a moving spot on a picture must be a moving object. A telescope can measure the image perfectly and still leave us with the wrong story if we identify the wrong thing inside that image. Near a black hole, moving almost at the speed of light, that small mistake can grow until it looks 50 times larger than the law it seems to break. The light still follows the rule. We are still learning what the picture means.